Very good morning, my dear students. Okay, coming to the fourth PPT. So here I am going to solve you some different types of problem. That is a type 3 problem. Okay, that is problems on what taper bar or varying cross section bar. Okay, so here it is similar procedure how we solved in the previous, that is a step down problem, but here we need to calculate the area first. Okay, if you know the area means you can get the what the answer. Okay, so as a in the formula only itself you know that what is a k is equal to ae by l, where if you know the area means then only you solve the problem. If you know the area means, if you not know the area means you have to calculate the first area. Okay, so here these are the same module 2 syllabus. Okay, so type 3 problem, so that is problems on taper bar, or it is also called as a varying cross section bar. Okay, so varying cross section bar means what? So it the diameter going to decreases. Okay, such type of elements you are going to call as a taper bar or varying cross section bar. Okay, so question they given like this: find the nodal displacement stress in each element and reaction at the fixed support for the thin plate of a uniform thickness of 1 mm. Okay, thickness is given for the 1 mm, and that is thickness is equal to 1 mm as shown in the below figure. Okay, take the Young modulus is equal to gigapascal, and weight density of the plate is equal to what? The density of the plate is given 76.6 into 10 to the power of minus 6 Newton per mm cube. In addition to the weight, it is subject to a point load of 100 Newton, and at the midpoint 100 Newton is force is acting here. Okay, model the plate with a 2 bar element. So you consider it as a 2 bar element, you have to calculate. That means what? This taper bar element you have to convert into step bar, then you go for doing the solve the problem. Okay, so if you before this, if you want to solve the any elimination bar element, you should know the Young modulus area and length, but here area is not given. Okay, instead of area they given thickness. Okay, you have to calculate the area first. Okay, so what is the first step? So you have to analyze the problem, read the problem carefully, and which is belongs to which type, and then we'll go for the calculation part. Okay, so this is a taper bar is given, so this is the larger side, this is shorter edge. Okay, so this side the length is what? 60 mm, that is a what? Width is 60, and this side is 30. Okay, this side is 30, and at exactly middle 100 Newton is acting. So it is not given kilonewton, you have to no need to convert here kilonewton. Okay, so they given only 100 Newton. Okay, at point 2. Okay, so first element 120 mm length is given, and second element length is 240, double of that. Okay, so here we need to calculate the area of what, then you have to okay, so first what is the first step? You have to note down the given data, convert into once, make it standard formula. Okay, so they given Young modulus for E is equal to E1 E2. So here the both the consider Young modulus E is nothing but the given E means you have to consider. Okay, suppose if they are given E1 E2 means you have to make separate one. Okay, so capital E is equal to E1 and E2, which is equal to 200 gigapascal and 2 into 10 to the power of 5 megapascal or Newton per mm square. Okay, thickness they given T is equal to 1 mm, thickness of this. Okay, so 1 mm they given, and length of element is equal to N1 and L2. If you divide 240 divided by means you are going to get half of that, that is 120. So L1 L2 is equal to 120 mm, and force at node 2. So this is a node 2, we have to 100 Newton they given, no need to convert here, and density rho is equal to 76.6 into 10 to the power of minus 6 Newton per mm square. Okay, these are the given data they given. Okay, first step for in the tapered bar or varying cross section bar, you have to convert the taper bar into stepped bar problem. So how to calculate that? We will move to this. Okay, that is the first number one. Step number one is you have to convert this FEM module into taper bar. Okay, so here look at this. Just to draw the diagram here, that is the first element, this is the second element. Okay, so area is given, area 1, area 2, and load is acting 100. This is the width of the given. Width of this element is equal to how much? They given width is this 60, and second width element is 30 given. This is width is given, this second element width is given. Okay, so this is element number 1, element number 2. Okay, they only telling that you have to consider this is the 2 bar element. Look at this, this is a very important sentence. This is okay, don't calculate the single bar element. They are asking what? Model the plate with a 2 bar element. Okay, so first you have to draw the step bar. Okay, the width is given, but we need to calculate what? L, that is what area we need to calculate. Okay, so L1 is given, L2 is given. So how to calculate? So look at this, you have to convert step bar into that is what? Taper bar into step bar first. Okay, so after calculating all those things, that is then go for calculate the area. Okay, so what is the area? How to calculate the area if the given width means? Okay, this is the formula. Okay, width of the plate at the center at node number 2 is equal to, what is the at the plate at center is equal to width, this is 60 plus 30 divided by 2, you are going to get the 45. Okay, 45 width you got the second. Okay, so average width of the plate of the above center is equal to 60 plus 45 divided by 2. You have to make it average, that is 60 plus this middle 45. Okay, so divided by 2 is equal to 52.5. So width you got Okay, so what is the formula for area? Area is equal to what? Width into thickness. So area of an element 1 is equal to width into thickness. Width we know this 52.5 substitute, thickness they given 1. So area for the first element is equal to 52.5 mm square, which is equal to A1. Similarly, you have to calculate the width, that is the second element area. So again, average width of the plate below the center, that is element 2, is equal to what? 30 plus 45. Okay, so first you need to calculate the width of the center, then you have to make it, add the average width. Okay, then take that width into thickness is equal to, which gives the area of an element 1. Similarly, area of an element 2 is equal to width, that is they will given 37.5 and thickness is given 137.5 mm square. Okay, area 1 and area 2. Okay, this is the only one trick to calculate the the area. Okay, if the given width. Okay, then remaining procedure is same. Now we know the area, that is you should if what is the formula, we already know young modulus they given, length is also given, then go for applying the procedure. Okay, same procedure. Okay, so since it is a 2D bar element, so how many nodes are present in this element? 3 nodes are there. This is node number 1, node number 2, node number 3. Okay, so element stiffness matrix is equal to what? The stiffness matrix for the bar element for the normally given by K is equal to AE by L 1 minus 1 minus 1 1. Okay, for element 1, so K1 is equal to AE by L, so A is equal to area 52.5 and young modulus is 2 into 10 to the power of 5 and length is equal to 120. Okay, you have to simplify this, you are going to get 0.87 into 10 to the power of 5, 1 minus 1 minus 1 1. Okay, so 10 to the power of 5 you keep as it is, then you have to multiply this 0.87 into this matrix, you are going to get 0.875 minus 0.875 minus 0.875 0.875. Okay, so here since it is belongs to one element, you calculated the one element, so one element is consist of node what? This is node number 1, this is node number 2, right here node number 1, node number 2, number 1 and 2. This is called as a global degree of freedom. Okay, so node number 1 1 2 1 2. Similarly, calculate the for element 2, this is the second element you need to calculate here. Okay, so second element is equal to, wherever K1 is there, replace K2 A2 E2 by L2. Okay, so substitute all the values, you are going to get the 10 to the power of 5 0.625 minus 0.625 minus 0.625 0.625. Okay, since it is a second element, in the second element nodes are presented what? 2 and 3, right here 2 and 3, 2 and 3. This is what called as global degree of freedom. Okay, so next, what is the next? Elemental body force of the vector. Okay, so how many elemental body force vector due to weight density? So here in the given question, the given density, that is weight density for the both the F1 F2 is equal to, we have the formula F is equal to AL FE by 2 1 minus 1. Okay, for element 1 is equal to F1 is equal to substitute all the formula, that is A1 area is given and the length formula, length value is substitute and F value substitute. Okay, divided by, that is F nothing but what? Density here. Okay, so density you have to substitute, divided by 2 1 minus 1, so you are going to get F1 is equal to 0.241 minus, that is what, 0 into, that is what, 0.241 0.24. this is belongs to one element. Okay, second element. Okay, also you have to substitute the second element, that is A2 L2 F2. Okay, weight density plays a major role in this problem. Okay, so weight density you have to calculate, you are going to get the F2 value is equal to 0.1723 and 0.1723. Okay, so since it is belongs to second element, right, the node number is 2 3, this is 1 2. Okay, so you calculated the F1 and F2 value. Okay, so now what is the global stiffness matrix? So global stiffness matrix is equal to what's combination of all those elements. Okay, K1 plus K2, so K1 plus K2, so K1 is, since it is a 3 node element are there, so you are going to get 3 into 3 matrix. First you have to write the 3 into 3 matrix, in the both the K1 and K2 10 to the power of common is there, according to the node number you have to add it. Okay, so node number 1 1, I will show one example here. So 1 1, you check 1 1 value in the both the matrices, what you calculated here. So 1 1, so this is 1 1, 0.875 1 1, it is not there, so 0.875 plus here not there, consider 0, so 0.875 plus 0 is equal to what? 0.875. okay, similarly like 2 1 2 1 2 1 is there, so here come 2 1 minus 0.875 is there, here not there, 0, so minus 0.875. okay, like that you have to substitute here, and 3 1 check both the matrices, that is K1 K2 is not there, consider 0. okay, like this you have to you have to add the both the matrix, that is K1 and K2, so you are going to give the what? Global stiffness matrix. Okay, then you apply the stiffness matrix for, that is what the properties of stiffness matrix here. Okay, the main diagonals are always positive, yes, this is always positive, and it is symmetric matrix, so minus 0 0 minus 3 minus 3.12. okay, so now it is this global stiffness matrix is correct. Then go for step number 4, that is okay, so also you have to calculate the nodal displacement vector, since it is 3 noded are there, so you Q1 Q2 Q3, these are the nodal displacement. okay, force value is there here, it is a summation of the point on body forces acting at the respective node, and it is given by, so since here the force 1, force 2, force 3, okay, so force 1, force 2 you calculated, okay, that is, and here also the point load is acting, so f1 you already calculated, f1 is equal to what, so you calculated here f1 is equal to 0.241 you substitute here, and f2 is equal to what, 0.241 plus f1 plus f2 plus f3, so this 100 Newton also you have to consider here, okay, so f1 is 0. All those things here, okay, so 0.241 and 0.1723 plus 100 Newton, combination of all those things, and 0.172, that is f2, okay, and which is gives the global load vector, so load vector you are going to get like this 1 2 3, okay, so here main thing is you have to add the f1 f2 f3 in the middle, because f1 f2 f3, so here f3 is given, you have to add here in this, okay, so finally you are going to get the displacement and f values, then apply the equilibrium condition. We know the equilibrium condition is equal to what, kq is equal to f, q stands for the displacement, substitute the values here, so k stands for global stiffness factor, substitute here, and displacement u1 u2 u3 and f value also substitute here, okay, so apply the boundary condition next. So apply the boundary condition, since in the given question, in the given diagram, node 1s are fixed, so delete first row first column. I will repeat again, node 1 is fixed in the given problem, so delete according to the elimination method of handling boundary condition, so first row first column you have to delete, so remaining is you are going to get 10 to the power of 5 1.5 like this you have to remain, okay, and solve this equation, you are going to get the q2 value and q3, that is the displacement at 2, displacement at 3, so 1.149 into 10 to the power of minus 3 mm, and q3 is equal to 1.152 into 10 to the power of minus 3, okay, so q1 is equal to 0 because it is fixed, so that is the nodal displacement are u1 u2 u3 or q1 q2 q3 is equal to, this is the final answer for the displacement for the given step bar, okay. Coming to the stress in each element, we have the formula for stress in each element is equal to what, stress is equal to Young modulus by LE minus 1 1 u1 u2, okay, for a first element the substitute the values Young modulus and length, okay, so minus 1 1 displacement is belongs to 1 element 1 2, okay, because why it is 1 2, for element 1 consists of node only 1 and 2, so take the 1 and 2 values, substitute, you are going to calculate, you are going to get stress for first element is equal to 1.915, okay. Coming to the second element, stress 2 is equal to 2 into, again substitute the values, here you have to consider the 2 and 3, this is very important here, so for first element 1 2, because the element 1 is consist of what, node number only 1 and 2, so second element 2 and 3, so if you solve this you are going to get 0.05 megapascal, okay. Coming to the support reaction, so already we have the formula, support reaction is equal to what, R is equal to kq minus f, substitute all the formula, simplify, you are going to get the reaction R1 is equal to minus 100.5678, so minus indicate what, the reaction is acting opposite direction, and R2 is equal to 0 and R3 is equal to 0, okay, at R2 R3 there is no any reaction, okay. So like this you have to solve the numerical problems on taper bar varying load, okay. So here it is similar all the problems, but in the taper bar section you have to calculate only this, okay, what, this one, how to calculate the area, okay, this is most important method. What this one, where is that slide gone, okay, this is very important here, okay. So if you calculate the area of each element, then remaining procedure is same, okay, since it is two elements are there, calculate the k1 k2, add, apply boundary condition, you are going to get the stress, strain, displacement and reaction, okay. So this is about the taper bar section. So in the taper bar they will give the width, you need to calculate the average width between, then calculate the area of element, okay, they given thickness, okay. So while calculating the force you have to calculate the density also you have to consider here, okay. So this is about the taper bar problem, okay, so in the module 2, okay. I hope you understand this problem, okay. Thank you very much.